So, welcoming everyone once again, and thank you for joining us today. I'm Eduardo Salazar from AMPL Optimization. I'm here with Professor Alexandra Newman from the Colorado School of Mines. And today we're going to walk you through a real-world scaling problem arising in steel production. We will cover the physical problem, the math behind it, and what it actually looks like when you implement something this complex in a modeling language such as AMPL. Before we dive in, I want to acknowledge the team behind this work. This has been a multi-institutional effort. Researchers at Universidad Adolfo Ibáñez in Chile, and several students and colleagues of Alexandra at Colorado School of Mines. In particular, Nelson Torres, a master's student at Chile, and his professor Eduardo Moreno. And in Colorado School of Mines, I'd like to specifically point out Jennifer McClary, whose computational work has been central to what you will see later. And this is very much a team effort, and Alexandra and I are just the ones presenting today. This is what the agenda looks like for the next 15 minutes or so. I'll start by setting the stage, what happens physically in a steel mini mill, and why scheduling it is so hard. Then Alexandra will take you through the optimization model and some of the results. After that, we'll come back together and I'll show you what this formulation actually looks like in ample code. And we will close with further analysis on the results and some reflection on what this means for our practice. Okay, so let's start with the big picture. The steel industry produces close to 2 billion tons of product every year, and nearly all of it goes through the processes that we're going to talk about today: continuous casting and hot rolling. These are not niche operations, they are the backbone of how steel gets made across many different industries. And yet, the way most plants schedule these operations is manual. You may have experienced schedulers with the rules of thumb or heuristics that have been refined over decades. But that works until it doesn't. And the gap between what intuition produces and what optimization can produce turns out to be quite significant. And that's what we're here to show you today. Before we go further, I would like to make sure we're all speaking the same language because this domain has its own vocabulary. So I will introduce some basic key terms. A heat is a batch of molten steel, around 160 tons held in a ladle. Each heat has a single chemical composition, which we call its grade. We can think of it as a recipe. It can be low carbon, medium carbon, high strength, low alloy. And once this steel solidifies, it goes through the casting process. It gets cut into slabs, and these slabs get rolled into coils, which is the finished product. Which are rolled to whatever thickness the custom ordered, and that thickness is called the gauge. And finally, we have also the cast width, the width at which a slab is actually cast, which can be wider than the customer's order if trimming is planned. There is a very clear distinction between the cast width and the order width, and that distinction is going to matter a lot when we get to the constraints. Now let me walk you through the physical process. In a mini mill, you start with scrap metal going into electric arc furnaces. You melt down this metal, you alloy it to your target chemistry, and then you have a heat of molten steel in a ladle. This heat gets continuously cast. The molten metal flows through a water-cooled mold, it solidifies into a strand, and you cut it into thin slabs. And here's the key part of this presentation. The facility we're working with today is a direct charge operation, meaning that the slabs go straight from the caster through a tunnel furnace and onto the hot rolling mill. There is no buffer, there is no slab yard where you can resequence things. What you cast is what you roll, in exactly the order you cast it, meaning that these decisions are physically coupled. The rolling mill then finally reduces each slab to the customer specified gauge through a series of roll stands, and the finished strip gets coiled up and shipped. And the no buffer part is what makes everything hard. We have some photos to give you a sense of the physical reality. On the left, we have a ladle of molten steel being tapped from the electric arc furnace. And on the right, we have a slab being cut from the continuous strand exiting the caster. This is hot, heavy, and fast-moving industrial equipment. When we talk about scheduling constraints later, keep in mind that the violations aren't just numbers in a spreadsheet, they have real physical consequences. And these consequences look like this. This is the most serious one. A cobble is what happens when the roll force, the gauge, and the speed are mismatched between stands in the rolling mill. The strip buckles and accumulates between the stands and produces this catastrophic failure. This is a real cobble. When this happens, the entire operation shuts down. It's a safety hazard for the people on the floor, and it takes hours to clear, incurring enormous economic losses. So when the model penalizes excessive gauge changes between consecutive coils, it's not an abstract function. It's preventing these cobbles from happening. Here's the layout of the facility. We have two casters running in parallel, a north caster and a south caster, both leading into a single hot rolling mill. The mill alternates. It takes one slab from the north caster and then one from the south, one from the north again, and so on. And because this is direct charge, there's no ability to hold inventory between casting and rolling. So you have two independent casting sequences that have to interleave into one rolling sequence, with no flexibility to rearrange anything after the fact. And this is the core tension, and I want to make sure it lands because it drives everything else in this talk. The casters care about chemistry. You want to minimize grade changes because switching between these stale grades, it produces intermixed scrap, which is an economic loss. We want long runs of the same grade within the same caster. On the other hand, the rolling mill cares about geometry. We have widths that should decrease monotonically to avoid edge defects. The gauge drops between consecutive coils need to be limited to prevent the cobbles I just talked about. And the widths coming from both casters, they need to be similar because they are alternating through the same rolling mill. In a plant with slab inventory, you could optimize this separately. First, you cast for chemistry, and then you resequence the slabs for good rolling geometry. But with direct charge, these decisions are coupled. We have to get both of them right at the same time. And the scale is not trivial. A typical daily schedule may consist from 100 to 200 coils across these two casters, multiple steel grades, and dozens of constraints. So as you can imagine, the combinatorial space is enormous. I will hand it to Alexandra so she can talk to us more about the problem.
Okay, so we have here a small example just to illustrate the complexities involved in scheduling. So the three main characteristics we consider with respect to the coils that we're going to sequence are the chemistry or grade, the width, and the gauge. And the idea behind these three is that grade cannot necessarily be easily transitioned from one type of chemistry to another. There's no such thing as like washing out the cauldron and restarting easily. So if you want to cast grade B followed by grade C, then the only way to do that is to blend B/C so that you have some intermix in between. So the idea is to not switch grades too frequently because that creates more intermix. And depending on the grades that follow each other, that could create a lot of intermix. And that would be theoretically have to be scrapped and sent back. The other two characteristics have to do with geometry. There's a grade consideration and a gauge sorry, a width consideration and a gauge consideration. So generally speaking, we want to cast wide to narrow, and generally speaking, we want to cast thick to thin. So if you consider the two casters, which is the usual we've been looking at with our industry partner, and then three grades, and we have just these 10 coils, you could see how we could take various sequences from caster 1 and caster 2. These converge onto a single roller. And so on caster 1, we've got a single grade change. On caster 2, we have a single grade change. We're casting wide to narrow and thick to thin per the specifications in the table. Now, these grades will converge from the caster. The coils will go onto a single roller. But you can see how if we alternate, which is what is usually done, coils from one caster than the other to go onto the roller to get fitted to the appropriate geometry after they're sufficiently baked, you can see that we have grade changes almost all the way through the sequence, even though on the caster, the grade changes were minimal. We do have a roller change, which then allows us to step up in gauge and width again. And so you can see that towards the end of the sequence there. So this is feasible, but you can certainly tell from a chemical standpoint that it would not be optimal. And we have far too many grade changes. And that's just 10 coils, not the usual 150 or so we might sequence at a time. Next slide. Next slide. So another thing we need to consider with respect to those rollers that we just saw on the previous slide is that every now and then they need to be changed out. That's because their lifespan wears just like a tire on your car would wear. And so they need to be ground down and sort of polished so they don't create defects in the steel. This is a very rudimentary model. We've been working on more sophisticated models, but it's essentially what we're incorporating right now into the optimization model. And it's simply that when you get close to 100% degradation, then you need to change your roller. Next slide. And so then with the grade changes, this is a little bit of an illustration of the intermix. So while we're never going to cast in a single schedule all of these grades simultaneously, we certainly are going to have these grade changes. So essentially, this is a color-coded visual of the amount of intermix from one grade to another. So you can see along the diagonal is green, meaning that, of course, you can cast from one grade to the same grade with no problems. Now, you can also see down near the so-called origin that there are a few grades that are actually quite favorable in terms of going from one to another. There's really negligible intermix. On the other hand, you can also see some red squares, meaning that those are considered radical. In other words, they really want to avoid those kind of grade changes if possible, and then the white boxes indicate it couldn't be done at all. Another thing you might notice that actually the table isn't symmetric. So changing from A to B is not necessarily the same as B to A. So these are some data we need to quantify and incorporate in the model as well. Next slide. So what we try to do essentially in English is our model determines the caster, roller, and slot for each scheduled coil. So in other words, if it's before the first roller change, then it's like the first rolling campaign. Before the second roller change, it's the second rolling campaign. The caster would be what bakes the material. And so recall there are two casters that simply go onto the same roller with a roll campaign with a roller that gets changed. And then we deskeratize, even though that's not the way it looks in the mill, but we sort of deskeratize each of these casters into slots so that we say that a coil is put into a slot, which is just a physical amount of space. Then the other nuance is that we have this continuous variable because we're allowed to cast wider than the order width. And that means that if you'd like to go from thick to thin and wide to narrow, you can't do much with a gauge, but in the latter case with the width, you can actually cast it wider and then you have to cut it down to the actual order width. Depending on the type of coil, you're either allowed to cast it wider or not, and there's different kinds of wider thans you can do, also depending on the type of coil it is and what the customer will assume. So there are quite a few nuanced rules around what it means to cast wider. So the objective contains many different terms, all of which amount to an aggregate minimizing badness of the schedule. So these are all elastic variables on specific constraints, allowing for the violation of a constraint with an appropriate penalty. And as you might imagine, getting the penalties correct with respect to what a mill operator might like is quite nuanced and an art in and of itself. So we want to minimize that intermix that has to do with the grades. We want to minimize large gauge drops between coils that sit adjacent to each other on the rollers. Otherwise, that could create a cobble that Eduardo spoke of earlier. We want to minimize that trim loss for the extent to which we're casting wider than the order width. We want to minimize the number of roller changes. So if you can imagine, you kind of don't want that knapsack constraint to have too much slack at the end. And so if you're not packing the right things in, you may get more slack and then have to change the rollers with a more life on them than you would like to, which then increases the overall number of roller changes. And then you want to minimize the width differences between coils and adjacent slots on different casters because they follow each other on the rollers. And so we really want to generally cast wide to narrow. If there's a slight increase, it's okay, but generally we're going wide to narrow. All right, so that's the objective. So then to go on to the constraint set, coils are cast, as we say, non-increasing, generally speaking, by width. Otherwise, you are allowed to trim them. There's three types of coils. There's a mill edge, which means that you cast either no greater than 0.5 inches above the order, or you can go between 1.5 and 6.5. And you might ask, well, what's the problem between 0.5 and 1.5? It's because the scissors do not have enough width to grip onto to cut the material off. So either you cast a 0.5 and that's equivalent to a hot rolled block, which essentially means that within this tolerances that engineers have specified, you're allowed to not be perfect, or you have to cast wide enough so the scissors can actually cut it. So that would be mill edge. Hot rolled block means no, you have to pretty much cast it within the specs. And the cut edge is between 1.5 and 6.5 inches. But you need to be a little bit more specific on that amount. All right, so the first slot on a roller has to be a sufficiently heavy gauge because of how the rollers kind of are tuned to squish the steel, and it's difficult to tune rollers for a very thin coil. That could create a cobble. So you want to have a thicker coil with more play for the force that's exerted. There has to be a decrease between adjacently cast coils that is within certain tolerances. So you can't jump down too much because then again, you have to worry about the force exerted to make that jump. And again, that could lead to a cobble. Rollers have to be changed after their lifespan has been expended. There needs to be equal length sequences on each caster. So every slot on one caster has to be juxtaposed with a coil on a slot on the opposite caster. There are certain coils that need to be cast in a certain position in the schedule because of these cleanliness considerations. Usually that means they're cast first in the campaign. And then, of course, each heat or amount of tonnage that we're kind of casting at one point, it's 165, 175 tons maybe, needs to be all of the same grade. So you can't be switching grades willy-nilly because the big cauldron that possesses that grade needs to have a minimum amount to be economically viable and reasonable logistically. And of course, there's a capacity associated with that cauldron, which is in technical terms called a ton dish. Okay, next slide. So we're not going to throw too much math at you, but just a little bit to give you a sense of the groups of elements we have and then the inputs and the outputs. So our basic model here is going to have groups of coils, grades, casters, slots, the types of coils we have, and then we're going to have subsets of coils on which roller changes can occur. Right, then we have inputs. And so our parameters, we have a lot of width-based parameters associated with the actual width of a coil and whether or not we go up in the width in order to actually have that cast width be larger than the order width to accommodate this wide to narrow scheme. We've also got degradation caused by a coil and the maximum degradation allowed. We've got some tons, so tonnage and a heat and tonnage of a coil, minimum max tonnage. We've got some chemistry considerations, the grade, and then the intermix associated with adjacent grades. And we've got some width, gauge based or thickness type of parameters associated with how thick a coil is, and then the various limits depending on what kind of coil we're looking at. So then the next things we'd like to talk about are variables. We've got some continuous variables here, which we're going to have in uppercase to distinguish from the parameters in lowercase. The continuous variables are black font, and they denote cumulative degradation on a roller, the cumulative tonnage of heat, and then the cast width, which could be greater than the order width. Then the binaries we're going to denote in red. So if a mill edge uses its alternative cast width bounds, If a grade change occurs between two successive slots on a caster, if there's a heat change between two successive slots on a caster, if a coil is assigned to a slot on a caster, and if there's a role change in a particular slot. Okay, so next slide. All right, so that's kind of the inputs and outputs you see. So the parameters and the variables, we spoke about the objective being that minimized set of badness. And then we have all the rules we spoke about earlier. So the models aren't really large. On the other hand, even with 150 coils, there's quite a few variables and constraints, as you can see simply by thinking about the rules and thinking about all the considerations and the various sets we have to include, and then the indices on the variables. You can see how that's going to create quite a large model, even with two casters and 150 coils and maybe 5 grades or so. So the 3 things we do, kind of color-coded, are first of all just to formulate the model efficiently. So ensure that we've got maybe a pretty tight relaxation. The variables are defined reasonably, maybe cut down on some of the integer variables too. Then we can eliminate some of the variables after we've kind of made the formulation. And finally, we've got some cutting plane ideas. So all of those things are going to be the subject of a little bit what I'm talking about next. And I want to emphasize that all of these things do make a big difference, from taking models that can't be solved at all to things that we're getting gaps. They're large, and we'll talk about how we've cut them down. But on the other hand, I want to emphasize we can do this all with an AMPL. So this is some fairly sophisticated modeling that we're doing in order to get models to solve more quickly, but it's all completely within the scope of a modeling language. And not only is it within the scope, it's very easily done. So it's not kludged. It's not what on earth is going on in this constraint. So I think that's important to note. So next slide. So first, to get to the variable elimination, so a natural sequencing formulation might want to track coils in successive slots. And so then you have a one coil, a successive coil, a slot on a caster. So that would have on the order of that number of binaries I have there. But we've actually cut down on that with some formulation that actually doesn't look at C squared, it only looks at C. The other type of variable we were able to eliminate, and Eduardo Moreno was quite good at seeing this, was for the coil, roller, slot, and caster combination. We've been able to shrink that down so we don't have variables carrying that number of indices either. So again, we can go from millions of variables to, tens or hundreds of thousands this way. And the next slide. Another type of variable elimination has to do with eliminating the roller index altogether and just tracking the degradation. And so if you know the degradation, but you don't have to say exactly what roller campaign, it doesn't really matter whether it's on the first or second campaign. It just matters how far the roller is to being degraded and needed to be changed out. So the consecutive coils, as I mentioned, that articulation can be sort of subsumed in some of the other variables, including continuous variables. And in this way, we can retain sort of a minimal set of binaries. And we have a paper on this, and so we're going a little bit fast on this concept, but I'm happy to discuss it later, or you can look. We've sort of taken time to explain this in the paper, but it's maybe not the first natural formulation, but it really made a difference. So on the next slide. Then we can also use these concepts that are very easily constructed in AMPL. I call them indexed sets. And what that means is it's a set with a subscript on it denoting elements of another set. So, for example, if you know something about the coils that can go in a particular slot, then you can eliminate some variable combination saying for the non-eligible coils to be cast in that slot. So you're going to restrict the set of slots based on the coils that can actually be cast there. And as I mentioned, we have some cleanliness considerations, so there are certain coils that can't go in certain slots. Also, you wouldn't change grades too early or too late in your schedule. If you change them too early, you don't have a full ton dish or cauldron's worth of material going onto the casters. So we can eliminate certain slots in which a grade change might occur. Again, this can be done with this construct that AMPL allows. And coil assignment. So all these sort of types of restrictions can be regulated through very simple and intuitive modeling constructs that AMPL allows for. So that was another key concept after just the model formulation, thinking about how we might reduce the number of variables. Right? So then if we go to the next slide, as Jeff Cam and his co-authors will note decades ago, and this is still an issue in industrial size models that we see, big M should not be too big. And so don't just put 9999 if you want to get rid of a constraint based on a certain binary variable value. So constraint 2D is telling us, it's a sandwich that says the width in a given slot on a given caster has to be between some bounds of a coil. And so, of course, it depends on the type of coil, and this is the mill edge coil. And so, if we cast that X variable, a certain coil C on caster K in slot S, then those bounds hold. The X is 1, the final term on the right-hand side drops out, and the width holds. If, on the other hand, X is 0 and we don't cast it, then the upper bounds are irrelevant for that particular combination of indices. And so we essentially want the upper bound not to hold. But that big M doesn't need to be more than a certain maximum width that W could ever assume. So you certainly don't want big M to be 1,000 because no coil is going to be 1,000 inches. So paying attention to things like that. Similarly, we've got in constraint 3D, these numbers are taken from the EJOR paper, that degradation needs to be greater than or equal to some maximum quantity, but it all depends whether or not you're actually changing out the roller on a given slot. So you're accumulating the degradation between a prior slot and what occurs on the present slot, being the ds minus 1 and the little d times the x respectively. But then that degradation all resets to 0 if indeed you've got a roll change. So you don't need, again, big M to be something crazy. You just need it to be 0 or below. And so if you just think about max degradation, the values that degradation can assume maximally, that would be your big M. So this is very important for regulating the logic of constraints and making sure your parameters make sense. Okay, and the next slide. So here are a few examples of some cuts that we introduced. So for example, if you look at the ceiling of the quotient of the degradation that a coil inflicts on a roller and the maximum degradation, that quotient is then going to be at least as many. So it's going to provide a lower bound on the number of roll changes. The next one would be the minimum number of grade changes that must occur. So in order to understand this constraint, let's say we have 2 casters and 2 grades. Okay, best case is you cast 1 grade on 1 caster, the other grade on the other caster. You don't necessarily need to incur a grade change. You probably will, but not necessarily. We're looking at theoretical bounds here. As soon as you bump that up to 3 grades and you've got 2 casters, you're going to need at least 1 grade change. Right? We can say similar things about heats, minimum and maximum. Number of times we're going to have a heat change over all the slots we're considering in a schedule based on the tonnage that is accumulating in the slot and either the minimum or maximum tonnage that we can have over that set of that schedule. Okay, so if we go to the next slide, we have a variety more cuts as well. Again, Eduardo Moreno was very good about finding some of these more subtle cuts. He introduced some new sets and parameters. And even though we have kind of expanded the model, quite a few more constraints, these cuts on imposing minimum bounds on the cost associated with a grade change and improving the bounds on the minimum amount of trim loss we'd have to incur. These were actually useful as well and easily put into the model via AMPL. Okay, so if we, next slide. So now I'll hand this back to Eduardo to talk a little bit about that implementation and how it's easy to do these types of things, both the modeling and then also the efficiency gains, all within the modeling language.
Thank you, Alexandra. So yeah, now that you have seen what the model decides and why those decisions are interconnected, we'll now take a look at how this translates into working AMPL code and what a modeling language brings to a problem of this complexity. We're going to take a look at 3 snippets from the actual implementation. The sets and parameters first. They have the domain knowledge encoded. Then the objective function, how the penalty structure gets readable. And finally, some of the constraints, not all of them, but this is where the real complexity lives. So this is these are the foundations. On the left, we have the ample declarations. We have the sets C, K, and S. They map directly from the mathematical notation Alexandra showed you. We have the coils, the casters, and the slots. This one-to-one mapping between the model and the code is not an accident. It is one of the main advantages of working in a modeling language. And there are two things I would like to highlight. First, we have the grade type set. This is a Dirac set or an index set that Alexandra spoke about. It dynamically extracts whatever grades are present in the data using seroff. So if you run this model on a Monday schedule with 3 grades, you will get one constraint and then, sorry, one set. And then if you model it on Tuesday with 5 grades, you will get a different set. The model adapts automatically. We don't change the code. The data change drives this change. And second, we have the C hat set. This is the set of coils eligible for a roller change. And the physical rule is that only coils with a gauge or above 0.155 inches can start a new rolling campaign. The way we encode this in AMPL is just with a single line. This set of C in C, which A of C greater or equal than A hat. In a solver API, you could do this maybe with a loop, building a filtered index list. This works, but it obscures the intent. So meaning that in a modeling language, this is done more easily. And then, for example, we have the objective function. Remember that this model minimizes a weighted penalty function. The sum of costs for the trim loss, the double trim loss, the grade changes, the intercaster width differences, the roller changes, the gauge drop, and the intercaster gauge differences as well. So in Apple, each of those operational concerns, they become a name variable. You can literally read the objective out loud and the plant manager will understand and can look and understand what's optimizing the optimizer. And this matters enormously for buying of these projects. The penalty weights depend to C, depend 5A, and so on. These are parameters that are tuned according to the plant engineers. These are calibrated on the fly, and they are not hard-coded numbers. If the plan decides that they want to penalize more heavily roller changes, then you can change one number in a single file and the model stays untouched. And then the elastic variables, the pos and neg variables, these implement the soft constraint structure. Some constraints in the model are hard. You physically cannot violate them. But on the other hand, you may have some soft constraints, meaning that you can violate those constraints, but violating so introduces a penalty. This is a clear distinction in practice, and in AMPL it's expressed quite naturally, as you will see in the following slides. We have some of these elastic constraints shown here, specifically the intercaster width difference constraint. As we have stated previously, both casters pour simultaneously into the same rolling mill. So you want the cast widths on the north and south casters to be similar. And the model allows up to 1 inch of difference for free, which is encoded in the W tilt parameter. Beyond that, every additional inch of difference costs $100 per the penalty table, which you will see in a bit. On the left, we can see the AMPL code. We have 2 constraints, one for each direction of the difference. The elastic variable pen to pos captures positive violations, and this other variable captures the negative ones. And together, we get the absolute value of with difference beyond the threshold. If we compare with the mathematical notation down here, we can see that we have this dotted less than symbol. It means a soft inequality. We can violate it at a cost. In AMPL, this is implemented by simply adding the elastic variable to the right-hand side of the constraint. And therefore, this penalty then gets put into the objective function, and this is how we penalize it. Obviously, also something I want to point out is that this nomenclature that we're using, the whole model, it comes from this reference, this EYOR paper. So if you're interested into reading more and seeing the complete model, you should look up this reference. We have more constraints. This is where the complexity really lives. We have the cast width constraints, which is the best illustration of how casting and rolling decisions are coupled. We have 2A, which is the monotonicity. On each caster, the widths should generally be non-increasing. The first constraint says that widths can decrease by up to W mil between consecutive slots. But if we take a look at 2A2, we can see that widths can increase, but only and only if a roller change happens at that slot, which we are getting with this ys+1 variable, which is the roller change binary if you recall the decision variables. So the width and the roller change decisions are directly linked. Now for 2D, we have the mill edge conditional bounds. This fires only for mill edge coils, and that condition is right here in this line of AMPL code. The binary variable BC it gives the optimizer a choice. It can use the standard bounds or it can opt for wider alternative bounds, which means accepting some trim loss but getting more flexibility in the overall schedule. And then the big M term in this 2D2 constraint. This is not an arbitrarily large number, as Alexandra has just discussed. It's derived from the physical process. It equals the maximum upper bound on any coil's cast width. And when the coil is assigned to that slot, when the coil is not assigned to that slot, the big M deactivates the constraint. And finally, just this last snippet is the grade change penalty, constraint 5A. This one is interesting because it has four index dimensions. We have the caster's K, the slot's S, and the two grade types. And the filters in the indexing expression handle the edge cases. We are going to skip the last slot, meaning when S is not equal to the cardinality of our set of slots, and when G1 and G2 are unequal. This operator may confuse some younger people, but this is basically the unequal operation. We have the filter zones inside the constraint body, the sum of the coil grade C and sum of coil grade C prime. They select only the coils of each grade, and AMPL will generate the correct constraint instance for every relevant combination of caster, slot, and grade pair automatically. And also we have the grade transition cost gamma. This is the heat map that Alexandra showed earlier, encoded as a data parameter. If a metallurgist revises the intermix tonnage range between grades, you can just update this gamma parameter on the data tables and the model code won't change. This is a constraint that in a solver API may result in multiple nested loops with conditional logic inside each one. And in AMPL, we have one declaration that reads very close to the math. So let's take a step back and ask ourselves specifically, well, why a modeling language? This model was originally prototyped in Python using Gurobi's API, meaning Gurobi Py. And this works definitely. You can build any MIP with a solver API. But for a formulation this complex with many interacting constraint families and with conditional logic and so on, and also with the strategies that Alexandra discussed, the cutting planes, and maybe even trying different solvers. A modeling language is definitely the right choice here because it provides you from things that you cannot get easily from an API. You get clarity. The AMPL declarations read like mathematical notation. You also get maintainability associated with this clarity. The penalty weights, the grade transition costs, the edge type rules, all of this lives in the data decoupled from the model itself and the code. And then you also get solver flexibility. Switching from Groovy to Simplex is one single line. When you're doing computational experiments early on your experimentation, and this problem may require them, this flexibility matters. The point is that AMPL is not the only way to do this. For problems of this complexity, the separation of model, data, solver, and complexity is what a modeling language provides as a practical significant advantage over a solver API. And I'll switch it back to Alexandra so she can talk to us more about the results.
Okay, thank you. So we used Gurobi 12. I mean, we are aware we now have Gurobi 13, so these results are just a couple months behind. So we turned off symmetry breaking and the solver generated cuts simply because we're doing that ourselves. And so we often find that with a tailored approach, what a solver will see in general that is a good thing to do is not necessarily as good as what the user can do in a tailored setting. This can be done with a single command in an AMPL command file, and so it's really very seamless to be able to do this and then impose our own sets of sort of efficiency uh, gain techniques. And so these instances, we're looking at 150 to 200 coils. Generally speaking, they've required hours of runtime. We are working on reducing that, and we'll talk a little bit more later. And then here is sort of with our industry partner, this is an instantiation, we'll say, of the penalties. You see here quite a few different penalties listed. I had 5 earlier. We've introduced a couple more for these particular cases we're running here. What you can see is that roller change has a very high penalty. Trim loss will also have pretty high penalty. You can see the grade change penalty is also there, equating that with trim loss. So we go to the next slide. So these are two schedules. One is something that the mill came up with themselves, and then one is something that the optimizer came up with, Ample and Garobi. And we are going to issue a disclaimer in this case, and things will get a little bit better if you wait a slide, but we've got a fairly large gap. So one math programming sort of characteristic that we found also with some healthcare modeling that was Candiano and I did is that when you have quite a few of these elastic constraints and you're trying to minimize the badness in the schedule, that can yield even with all the best intentions, still a loose bound. So we think our gap is more the result of a loose bound than anything else, and we have some computation that might sort of show that in the eJOR paper. But suffice it to say, you can see what the optimizer can do that someone with years of mill experience cannot. So we've got in 3 red boxes on the left-hand side, a late roller change, right? So that we might have had a little more degradation on the roller than we should have. And we can also see slots without coils and unnecessary grade changes. Let me back up a step just to explain these plots. So what we have here at the very top is each slot, and that's one of those little squares. And the color of the square indicates the grade. And we've got 2 rows of them because we have 2 casters. And so you can see the slots, and you can see what's juxtaposed one slot compared to the other, just by what's kind of in sort of directly vertical lined down. All right. So that sort of explains the slots. You can see that some of them simply they didn't cast anything in them. So that's kind of a violation of their practices. Now, the other thing is we have a primary axis on which we denote the width. And we've got 4 different denotations of width. We've got 2 from each caster. And what is actually in the solid sort of lines as opposed to the dots is what was cast. And then what's in the circles, either the open circles or the black circles, is what was actually ordered. And so whenever you see that order below the cast, you can see that there's trim loss. And you can see quite a bit of trim loss then towards the end of the schedule as well there after the second roll change. The vertical purple lines are the roll changes. And then we have a secondary axis. That's blue, labeled in blue to match the blue, and that's the gauge. So that's the thickness. And so you can kind of see how the thickness is going down. So wide to narrow, then it can go back up to wide when we have one of those roll changes. So the badness consists of late roll changes, slots without coils, potentially unnecessary grade changes. And you can also even nitpick and say there is, a bit of a trim loss as well after that second roller change. So I mean, these are just scaled kind of values here based on those penalties you saw in the earlier slide, nearly $27,000. We get that down to 17,000, even with that wide gap. All right. And you see that we've actually eliminated grade change. We do still suffer from some significant trim loss, and we do have a gauge drop that's fairly large and that the mill wouldn't necessarily like to see off in that box C. But given the penalties and the relative weightings, this is still a better schedule on the right that the optimizer has been able to derive. Now, if we go to the next slide, this is where things kind of get quite interesting because sometimes solving an optimization model has nothing to do with optimization. And so Jen had a very good insight on this model. She's one of my current PhD students and a U.S. Army officer. And so she said, let me take a look at all the the characteristics of all the coils that the mill gave me to schedule. And so we have three grades, and she looked at the width, the gauge, and the weight. And you could kind of see that grade two and maybe a little bit grade three just behaving a bit badly there, right? So we've got widths that are quite a bit thinner in certain for certain coils. And then we have some gauges that are quite a bit thicker than certain coils. And then we have some tonnage that's quite a bit heavier. And you might say, well, tonnage is tonnage. But the thing is that when you have large boulders to put in your knapsack, it makes things a little bit difficult, to fit everything else, the medium-sized rocks around it. So, those are things we also have to watch out for. So what she did is she said, I will take away 14 coils that seem to be a nuisance and they're just outliers. And you can see now there's a dramatic reduction in that trim loss. So those really thin coils, those ones with this very small width, some of those she just got rid of and said, you know what, these are not good in the schedule. And so you can see where that trim loss really then decreases. And so we wind up, the real badness in the schedule is simply with a large gauge drop there. That's it. So the cost is about half that, is what you saw on the previous slide. We're also getting much better gap because now the solver isn't trying to trick us into thinking that it really can get, that good schedule that is absolutely only theoretically possible and practically remains elusive. Now, one other thing just to mention is you might say, well, someone's got to cast those 14 coils at some time. So, you're just kind of cherry picking and moving the problem down the line. And we contend that is not true. We're still working on sort of our selection methodology, but just because those thin coils were no good in the schedule doesn't mean they're not good in another schedule where there's more thin coils. And so it's nice to be able to say, well, we're just going to group these with a different schedule that's more suitable. It's kind of like if you have cars on the highway, maybe you don't want like the combine driving down the highway with, a passenger vehicle. There's nothing wrong with the combine, it just doesn't belong on the highway. Don't mix it with that. It goes on a different road, right? So that's kind of our notion here. All right, so next slide. So just to summarize a little bit, I do want to absolutely emphasize the role that Professor Brian Thomas played. This is his continuous casting consortium, of which we are sort of tagging along as a part. For non-operations researchers, you might be interested to know, I mean, this professor worried for years and years about, why there are bubbles in his steel and what kind of pressure should the water jets be exerting on the coils to cool them and so forth. So all these kind of really thermomechanical questions. And when he was a professor at University of Illinois for a long time, came here to School of Mines, and I said to him, you must have an optimization model in that mill. He said, well, we do. And so we've been working with this mill ever since. And so there's been a big learning curve, but I would also say that if you think that you don't have an optimization problem hiding around the corner, anything has an optimization model. So if you're a real optimizer, great way to take advantage of something like this is indeed to use modeling language and tools that are easy to develop your models. But it's a difficult problem. We also have a heuristic we've developed. It's got some challenges. We've just very recently been working with someone from Technische Universität Dresden, and he's just hot off the press gotten us a new heuristic, but that's going to have to obviously play together with the optimization model. So it's not to say that heuristics don't have their place. But regardless, we're still having some difficulty with the optimization. There's a lot of interesting operations research challenges more broadly. There's also statistical questions as well. And then the statistical models in turn can be fused into the optimization models that will only make the scheduling better. So the applied work is definitely quite difficult, but it can be rewarding when you actually get a schedule back from the mill when they've looked at it, tweaked it, and they say, "Oh wow, we think we might be able to use this." So I think I'll turn it back over to Eduardo for some closing remarks.
Thank you, Alexandra. Yeah, so let me close with four takeaways, specifically for the students and early career practitioners in the audience. First, as you have seen, real problems resist clean decomposition. In a textbook, maybe they will model casting and rolling separately, but in this plant that fails because it produces invisible schedules. The coupling between chemistry and geometry isn't optional, it's physical. Second, the formulation is where the hard work happens, as Alexandra showed, through techniques such as variable elimination, type eigenvalues, custom coding planes. These are what made the problem tractable. The solver is powerful, but it's not almighty. It will not do this for you. Third, the modeling language definitely bridges the gap between the math and the deployment. The AMPL code maps as close as one-to-one with the formulation. Plant engineers can read the penalty structure and they can understand it. And the research team iterates on the formulation on the same file, the same language with any solver. And lastly, the model will outlive the project, meaning that new grades will get introduced, the penalty weights will get recalibrated, the plant will try a different solver, the data may change, but the formulation stays. And this is how academic work actually becomes industrial practice through this durability. Um, and I guess that's all for us today. Thank you all for your time today. This has been a great collaboration, and we're excited about where this work is going. If you'd like to explore AMPL, you can reach out to ampl.com. For more examples, you can visit our repository of examples at colab.ample.com. For our specific academia offerings, you can visit ample.com/academia or reach out to the mail academia@ample.com. And obviously, if you want to reach out to Alexandra and or me for more questions, comments, and collaborations, please feel free to email us in these addresses.